All right, so for nonlinear dimension reduction, the purpose is visualization. And in the whole CRAP pipeline, it is at this step. After you cluster your cells, you want to visualize the cells in the 2D space because we cannot see more than 3D. And if we don't do the dimension reduction, right now every cell is in the PC space. Depending on how many PCs you decide to keep, the PC number can typically range from 20 to 50. So here the question is, we cannot visualize the PCs because they are too, let me see, because they are too high dimensional. So therefore, we have to do a projection to 2 dimensions. So in Surat, and the default is UMAP. You can run UMAP, but earlier people also use TSNE. So in Sierra package, you will have a function called run UMAP or run TSNE. And here, the dimensions 1 to 10 means the number of PCs you use as input into UMAP. This means that you are going to use 10 PCs. And once you run the UMAP, then you can plot this dimension plot. So essentially, it will give you something like this. So you will see 2 dimensions UMAP provides, and in particular, here the colors are your cell cluster labels. So you see that this is one color, right? One cluster, and this is another. So in total, here you have 9 clusters because the numbering starts from 0. So you're just showing the 9 clusters. A very common misconception is that some people claim UMAP to be a dimension or to be a clustering method, but that's not the case. UMAP doesn't perform the clustering. The clustering was performed by you before you run the UMAP by, for example, by the Louvain clustering or Leiden clustering in Surat. And you're just showing the cells locations with their labels, and the labels are already provided. So basically, you never want to say UMAP is a clustering method. That's just a misconception. Okay, it's a visualization method. All right, and you see in run UMAP function, there are a few key parameters. The 2 most important ones, the key, how to say, hyperparameter that determines the UMAP result is the number of neighbors and the number and the minimum distance. So these are 2 key parameters, hyperparameters needed in the UMAP method, which we'll introduce later. So the n.neighbors parameter determines the number of neighboring points used in local approximations of manifold structure. Larger values will result in more global structure being preserved at the loss of detailed local structure. So in other words, if you set a large number of neighbors, you are considering larger neighborhoods, and you will lose some of the local small clusters, but you will better preserve the overall relationships among the cells. In general, this parameter should often be in the range of 5 to 50. Minimum distance is another parameter that controls how tightly the embedding is allowed to compress points together. Larger values ensure embedded points are more evenly distributed, while smaller values allows the algorithm to optimize more accurately with regard to local structure. So sensible values are in the range of 0.001 to 0.5. So essentially, you want to use this to control how the points are distributed in this local cluster. For example, when they're evenly distributed or they're tied together. So if they are tied together, then you may see some local structure more clearly. But there is a risk of the so-called overplotting, that the points may be overlapping each other. So these 2 parameters need to be set, and these are the default. Okay, and also, and in the input, you will need to input number of dimensions times, basically right here, 1 to 10, number of dimensions. And this is which dimensions to use as input features. And in our case, since you set the reduction to PCA, it means that you're using the PC1 to PC10. But you can also set it to ICA. If you perform ICA on your data, then you will use the independent components, ICs, instead of PCs. And also for features. So basically, if you set the features to be some values, then UMAP will be wrong on these set of features instead of PCs. For example, if you set the features to be a few genes, maybe 10 genes, then the UMAP will be wrong on these 10 genes instead of the PCs. So these are just the input you can specify. So first of all, before we talk about t-SNE and UMAP in detail, we'll talk about some of the earlier methods that performs this nonlinear dimension reduction. So interestingly, in 2000, in the same issue of Science, two nonlinear dimension methods were published back to back, because at that time, nonlinear dimension reduction was still a new concept. Okay, the first one is called ISOMAP. Basically, it's a generalization of the MDS method we talked about. So do you still remember what is MDS? We try to preserve the distances, right? The input distances in 2D. So hopefully that the 2D Euclidean distances resemble the input pairwise distances. Okay, so what ISOMAP does is the input distance is the geodesic distance, and we will define this. Okay, so let's just read this abstract together. Scientists working with large volumes of high-dimensional data, such as global climate patterns, stellar spectra, or human gene distributions, regularly confront the problem of dimensionality reduction, finding meaningful low-dimensional structure hidden in their high-dimensional observations. The human brain confronts the same problem in everyday perception, extracting from its high-dimensional sensory inputs 30,000 auditory nerve vibes or 10 to the 6 optic nerve fibers, a manageable small number of perceptually relevant features. Here we describe an approach to solving dimensionality reduction problems that uses easily measured local metric information to learn the underlying global geometry of a dataset. Unlike classical techniques such as PCA and MDS, our approach is capable of discovering the nonlinear degrees of freedom that underlie complex natural observations, such as human handwriting or images of a face under different viewing conditions. In contrast to previous algorithms for nonlinear dimensionality reduction, ours efficiently computes a globally optimal solution, and for an important class of data manifolds, is guaranteed to converge asymptotically to the true structure. Okay, so first of all, PCA and MDS. Let's do a quick review. PCA and MDS are simple to implement, efficiently computable, and guaranteed to discover the true structure of data lying on or near a linear subspace of the high-dimensional input space. For example, if you have data points in a 2D space that lie perfectly on a line, then you just need a line to represent the data, and that line is a linear subspace of the 2D space. PCA finds a low-dimensional embedding of the data point that best preserves their variance as measured in the high-dimensional input space, right? Variance preservation. Classical MDS finds an embedding that preserves the interpoint distances equivalent to PCA when those distances are Euclidean. So this is what I said. If you have data, tabular data, say n data points in p dimensions, you first compute the Euclidean distances in the p-dimensional space. You run MDS to find the two-dimensional representation, and then that two-dimensional representations or embeddings are just the top two PCs of your PCA. That's it. However, many data sets contain essential nonlinear structures that are invisible to PCA and MDS. For example, both methods fail to detect the true degree of freedom of the face data set. And so before we show the face data set, let's look at the Swiss roll data, the famous example. So here you see the data points are lying on the Swiss roll in a 3D space. In this case, the subspace is two-dimensional, right? The Swiss roll just have a surface to roll together, but it's not linear in the 3D space. So in this case, for two arbitrary points here and here, on a nonlinear manifold, their Euclidean distance in the high-dimensional input space, the 3D space here, may not accurately reflect their intrinsic similarity, because you see the Euclidean distance is actually short between the 2 points, but the distance following the manifold is long, right? So in this case, the Euclidean distance doesn't reflect this. And so what do we do? So the distance the 2 points follow, the shortest distance between 2 points within the manifold has a definition, has a term called geodesic distance. Yeah, so in this case, the solid curve is where the geodesic distance is measured. Yeah. Okay, so for those of you in the class, it will be great if I can see your faces. Right now, I'm only seeing one person among all of you, because otherwise it feels like I'm just talking to the screen. Okay, thank you. So nonlinear manifolds and geodesic distance. A nonlinear manifold is a topological space that locally resembles Euclidean space that may have a more complex global structure, like the Swiss probe. Unlike a linear manifold, which is flat, a nonlinear manifold can be curved or twisted in various ways. Then the geodesic distance between 2 points on a manifold is the shortest path between them that lies entirely on the manifold. It generalizes the concept of straight line distance to curved spaces. Okay, so then isomap algorithm. So the first step of the algorithm is to determine which points are neighbors on the manifold M based on the distances dxij between pairs of points ij in the input space X. Okay, input space is X, and we will have 2 data points I and j. 2 simple methods are to connect each point to all points with some fixed radius epsilon. So this approach is called the epsilon bow approach, or to all of its k nearest neighbors. That's called KNN approach. These neighborhood relations are represented as a weighted graph G over the data point with edges of weight dxij between neighboring points. So essentially, you see, here we have the data points, and each point is connected to its local neighbors. So basically, you can define the local neighbors in 2 ways: by a bow with a fixed radius epsilon. That is, this point is connected to all data points whose distances are within epsilon to it. Or you can just simply connect the points to all the KNNs, K nearest neighbors, either way. Right, so you just want to construct this graph. So the KNN approach guarantees that each point is only connected to K neighbors, but the epsilon approach may differ, right, depending on how dense this region is with data points. If it's very dense, then within the epsilon bow, you may connect the point to many points. Otherwise, if the region is very sparse, you may only connect the point to very few data points, or even none. Okay, so you see, this is the graph we constructed for the Swiss roll data with k equals 7, and there are a total of 1,000 data points. And you see, by restricting this k equals 7, essentially, we don't have data points across the manifold to be connected by Euclidean distance, right? We don't have this case. So this point is not connected to this because it's too far away. It's not within the 7 nearest neighbors. And then you can see this graph well represents the manifold, right? So this first step is graph construction, using local neighborhood connectivity to get this local structure. In the second step, you will basically estimate geodesic distance using the graph. So what is the idea? So since every point is connected to one more point, right? Every 2 points on the manifold must have a path that you can go from one point to another point to another point until you reach this point. And the shortest path in this graph is used to approximate or estimate the geodesic distance. Yeah, so basically you find the geodesic distance between 2 points, which are, and the shortest path follows the red line. And then the final step is to apply MDS to the geodesic distances. In this case, they are approximated by the graph distances referred to as dgij. Okay, so dgij is the graph distance, which is supposed to estimate or approximate the manifold geodesic distance dmij. So dmij is the true distance we hope to get, but we don't know it because we don't observe the manifold. So the approximate version is the dgij. Okay. So finally, MDS apply to dgij, so you can visualize the points in 2D in the hope that their 2D Euclidean distances will mimic the graph distances. Okay, so this is the example output by isomap. So it's a two-dimensional embedding recovered by isomap in step 3, which best preserves the shortest path distance in the neighborhood graph. So basically, you're showing the nodes in 2D, and the red path still reflects this red path, okay? Because we have these points, and we can connect them. And this blue thing is the 2D Euclidean distance. And the idea is just to argue that, oh, the 2D Euclidean distance will approximate the graph distance we obtained on the manifold. Okay, so essentially, you see, even though your data point in 3D looks like a Swiss roll, but in 2D, isomap shows a flat space, which is what it's supposed to be, right? The manifold is flat. Okay, so this is isomap. It is basically MDS applied to geodesic distance, and the approximation of geodesic distance goes through this graph construction. Does that make sense? You first construct graph, and then you find the shortest path. All right, so this is just more details about the final step. The final step applies classical MDS to the matrix of graph distances, constructing an embedding of the data in a d-dimensional Euclidean space Y. So typically D is equal to 2, two-dimensional space, that best preserves the manifold's estimated intrinsic geometry, which is by the graph. The coordinate vector yi for points in Y are chosen to minimize the cost function, where dy is the matrix of Euclidean distances in 2D, and this one, L2 norm, we have seen this by L2 matrix norm. The tau operator converts distances to inner products. So which is what we showed you before. We basically decompose that gram matrix so we can get y as the coordinates. We are trying to get the y transpose, so to get an n by n gram matrix. If you check the lecture notes, we did that, which uniquely characterize the geometry of data in a form that supports efficient optimization. The global minimum of this equation 1 is achieved by setting the coordinates yi to the top d eigenvectors of the matrix tau g. Yeah, that's what we did. You get an input data, the distance matrix, convert that to gram matrix, and then you do eigen decomposition on the gram matrix. As with PCA or MDS, the true dimensionality of the data can be estimated from the decrease in error as the dimensionality of Y increases. So in other words, the higher dimension of your Y, the better approximation you can get. But we're only able to visualize 2D or 3D, right? So the dimension of Y cannot really be greater than 3. Otherwise, you lose the purpose of doing visualization. For the Swiss roll, where classical methods fail, the residual variance of isomap correctly bottoms out at d equals 2. So basically, you can choose 2 dimensions. Okay. Again, this is a summary of isomap algorithm. We already said that 3 steps. Construct a neighborhood graph, compute the shortest path between 2 points along the graph, and then construct d-dimensional embedding or 2-dimensional embedding by MDS. Any questions before we move on, before we leave isomap? Because that's the first method we'll talk about today. All right, if not, then applications. So interpolations along straight line in the isomap coordinate space. So basically, we want to look at these 2 things, right? So the images for the first row, it's just turning from left to right by turning the direction. And this one is turning from up to down to another direction of orientation change. And this is another example where there's a consequential movement of your hand, right? So this is like you basically you go from a fist to a hand, extended hand, and this is you change your direction of your hand. And so this is some handwriting for numbers, which is a very classical example for doing computer vision machine learning, right? So these are different ways to write too. So essentially, if you look at the paper, basically for these cases, you will see that the dimension, the embeddings of isomap 2D embedding can put these images in a sequence. So they follow the same order as in the original interpretation. Well, if you use classical method, then it's not so good. Yeah, so these are just applications. Okay, on the same issue of science, there's another nonlinear dimension method called local linear embedding, LLE. Okay, let's also read the abstract. Many areas of science depend on exploratory data analysis and visualization. The need to analyze large amounts of multivariate data raises the fundamental problem of dimensionality reduction. How to discover compact representations of high-dimensional data. Here, we introduce LLE, an unsupervised learning algorithm that computes low-dimensional, neighborhood-preserving embeddings of high-dimensional inputs. Unlike clustering methods for local dimensionality reduction, LLE maps its inputs into a single global coordinate system of lower dimensionality, and its optimizations do not involve local minima. By exploiting the local symmetries of linear reconstructions, LLE is able to learn the global structure of nonlinear manifolds, such as those generated by images or faces or documents of text. Okay, again, a Swiss roll example, a typical example for manifold learning, right? We want to find this. So essentially, you want to preserve the local neighborhoods, local linear embedding. In other words, here the name stands, we want to look for local neighborhood. In the local neighborhoods, we want to have a linear combination of neighbors to represent the data points. Here's the detailed explanation. Here, we take a different approach called LLE that eliminates the need to estimate pairwise distances between widely separated data points. Unlike previous methods, LLE recovers global nonlinear structure from local linear fits. So you don't need to compute the geodesic distances anymore. The LLE algorithm summarized in figure 2 is based on simple geometric intuition. Suppose the data consists of n real value vectors xi, so I goes from 1 to big N, each of dimensionality big D, sample from some underlying manifold, provided there is sufficient data such that the manifold is well sampled. Yeah, so you don't want the case where the data is the sample size is so small you miss certain parts, right? There's no data coming from that part, and you cannot do anything. We expect each data point its neighbors to lie on or close to a local linear patch of the manifold. So in other words, you're hoping that in this local neighborhood, the 2D space, subspace here is close to linear, a surface, a flat surface. So this is the idea of Taylor expansion. You're trying to approximate this local thing by a flat or linear thing. Oops. Okay. We characterize the local geometry of these patches by linear coefficients that reconstruct each data point from its neighbors. Reconstruction errors are measured by the cost function. So essentially, you see data points J are in the neighborhood of data point I. So we are trying to represent or reconstruct data point Xi as a linear combination of data points J in the neighborhood. So every data point J receives a weight Wij. Yeah, that's it. And we are trying to minimize this for all data points I, not just Xi only, but other I's. Okay. But you know, the weights are from I to J. So specifically, every data point J has a weight for I specifically, and which adds up to the square distances between all the data points and their reconstructions. The weights Wij summarize the contribution of the jth data point to the ith reconstruction. To compute the weights Wii to itself, we minimize the cost function subject to two constraints. First, that each data point xi is constructed only from its neighbors, enforcing Yij equals 0 if xj doesn't belong to the set of neighbors of xi. Second, that the rows of the weight matrix sum up to 1, Wij sum up to 1 across j for a given I. The optimal weights Wij subject to this constraint 6. Constraint 6 are found by solving a least square problem 7. Okay, so that's for the original dimensions. We haven't done dimension reduction yet. This is in the original D-dimensional space. Then LLE constructs a neighborhood preserving mapping based on the above idea. In the final step of the algorithm, each high-dimensional observation xi is mapped to a low-dimensional vector yi, representing global internal coordinates on the manifold. This is done by choosing a small d-dimensional coordinate, so typically small d equals 2, yi to minimize the embedding cost function. So remember, note that here we have the same Yij, which are what we learned from the original high-dimensional space, but we're trying to find the Yi's, the two-dimensional embeddings. This cost function, like the previous one, is based on locally linear reconstruction errors, but here we fix the weights Wij while optimizing the coordinates Yi. The embedding cost in equation 2 defines a quadratic form in the vectors yi. Subject to constraints that make the problem well posed, it can be minimized by solving a sparse n by n eigenvalue problem, whose bottom d non-zero eigenvectors provide an ordered set of orthogonal coordinates centered at the origin. So in other words, what you're trying to do here is that given the W matrix, the weights you learn from here. And what you can do is that you can perform eigenvalue decomposition to get the Y's. And you will need to pick the bottom D, the bottom two, if D is equal to 2 dimensions, non-zero eigenvectors, non-zero eigenvectors, and find those as your y1 to yn. So in other words, you will start from high dimensional data to get W, and then from W, you will get a Y's. So maybe we can take a look at here. The steps of local linear embedding. First, assign neighbors each data point xi. For example, you can also use KNN. You select the neighbors. Here, the black dot is xi, the gray dots are the neighbors. Second, compute the weights that best linearly reconstruct xi from its neighbors, solving the constraint linear least square problem in equation 1. So you get the weights for all these neighbors. 3, compute the low-dimensional embedding vectors yi best reconstructed by Wij. So given the same Wij here, you'll find the W's. Minimizing equation 2 by finding the smallest eigenmodes of the sparse symmetric matrix equation 3, which we're not showing here. We're just giving you the high-level idea, but you can check the paper for details. Although the weights Wij and vectors Wi are computed by methods in linear algebra, the constraint that points are only reconstructed from neighbors can result in highly nonlinear embeddings. Yeah, so essentially, basically, you're doing something sort of like PCA, but in a very local way, right? You're doing the linear dimension reduction in a local way, but you are not preserving using all n data points because there may not be a linear subspace. Okay, that's the LLE algorithm. And using this, you can see that, and this is also a very typical strategy, right? For studying a nonlinear function, we use local linear approximation. This idea is also very general. So this one's showing for the face images, and these dots are the 2D embeddings. And we can see that following some path along the 2D embeddings, we can see some gradual changes in the facial expression, suggesting that the embeddings are themselves meaningful. Yeah, so that's LLE. All right, some comparisons between the two, isomap and LLE. So our goals are similar, but with slight differences because they're both nonlinear. Isomap aims to preserve more of the global geometric structure. So that's why your graph represents the whole manifold. While LLE preserves local geometric structure because every reconstruction happens locally. And isomap constructs a neighborhood graph using k-nearest neighbors or fixed radius epsilon. While in LLE, you just use the KNN to define the neighborhoods, so you can learn the weights. Distance metric measure. So it uses geodesic distances, the shortest path on the graph, while LLE doesn't use distances directly, right? Because we're doing the reconstruction. You see, there's no computation of the distance, pairwise distance, but we're just trying to reconstruct xi using neighbors, just getting the weights. And with the weights, we try to find the data points in 2D. We're not doing any distance calculation. Embedding technique. For isomap, it applies MDS to the geodesic distance matrix, while for LLE, it minimizes reconstruction errors of local neighborhoods. Advantages. Isomap captures global data structure good for data with significant curvature, like the Swiss roll. LLE captures local data structure well, effective for data with locally linear structures. Disadvantages. Isomap can be computationally intensive because you will need to compute the n by n geodesic distance, right? That's quite something. You have to do that for every data point pairs based on the graph you construct. For LLE, it's much faster because for every data's reconstruction, it only involves its local neighborhood with k neighbors, nothing beyond that. It is sensitive to, however, it is sensitive to noise, and it can struggle with large-scale structures because it's only local. Okay, so there's no perfect method. And these are the classical ones published in 2000 on the same issue of Science. So more recent methods include SNE, t-SNE, and UMAP. At the end of our last lecture, I briefly talked about SNE, right? We've just started talking about SNE a little bit. I said that we're not trying to preserve the pairwise distances anymore, but we're trying to preserve some distance converted density functions. So you can see this is how they change from SNE to t-SNE to UMAP. So they also follow a logic in their development. So it is worth noting that at the onset that the academic papers introducing these techniques, SNE, stochastic neighbor embedding, by Geoffrey Hinton and Sam Roweiss, t-SNE, visualizing data using t-SNE by Lawrence van der Matten and Geoffrey Hinton, and UMAP by these people. So UMAP, it's interesting that the paper that proposed the method remains unpublished. It's still like a preprint on arXiv. However, the package has been widely used and the biological application has been widely used. These are worth reading in full. That said, these are dense papers. This lesson is intended to be this is from this blog, you can check it out, to be a digestible guide, maybe a first step before reading the complete papers for time-strapped machine learning practitioners to help them understand and the underlying logic and evolution from t-SNE to SNE to t-SNE to UMAP. Okay, so essentially, you want to first have an embedding for the images. So you may encode each image as a long vector. So for example, you may have the sign, stop, English, symbol, octagon. So you can give a value for each dimension to describe one image. And then suppose that the embeddings are reasonable. You want to project them to 2 dimensions to visualize the relationships among the data points. Okay, so dimension reduction plays an important role in data science as a fundamental technique in both visualization and pre-processing for machine learning. Dimension reduction methods map high-dimensional data X into lower-dimensional data Y, with n being the number of data points. So the notation we have seen before. So the essence of computing tech embeddings is a form of dimension reduction. When working with unstructured data, like images, the input space can contain images of size WHC with high channels, tokenized language. This is what natural language processing is doing, audio signals, etc. So these are all called unstructured data. For instance, let the input space be composed of images with resolution 1024 by 1024, the number of pixels in row and the column. In this case, the input dimensionality is larger than 1 million, because if you take the product, that's the number of pixels. Let's assume you use a model such as ReNet or EfficientNet, so two neural networks, and extract embeddings with 1,000 dimensions. You get the embeddings from the neural network. In this case, your output space dimensionality is 1,000, 3 orders of magnitude lower. You already did some dimension reduction from the pixels to some embedding dimensions. This transformation turns the very large, often sparse input vectors into smaller, still of considerable size, dense feature vectors or embeddings. Hence, we will refer to the subspace as feature space or embedding space. So these are the features we will use for doing the visualization before we run t-SNE neural map. There are extensive amount of dimensionality reduction techniques. They can be grouped into 3 categories: feature selection, matrix factorization, and neighbor graphs. All right, we talked about the first 2. Feature selection is like our highly variable gene selection. Remember that. So we're selecting certain genes that meet our criterion, like large variants. Then we only use that subset of features. That's feature selection. For matrix factorization, we have talked about PCA, GLM PCA, and also something following that, right? We have the NMF, PNMF, and also we have the let me see. I wouldn't call ICEF matrix factorization. Yeah, NMF, PNMF. So basically, you want to decompose the matrix into some product of 2 matrices, and because of the linear algebra operation involved, so such dimension reduction is linear. So each new dimension is a linear combination of the original dimensions. So for the latter category, neighborhood graph is what we'll talk about today. So you can see that for both the ISOMAP and LLE, they use neighborhoods. So basically, if you want to go for nonlinear dimension reduction, neighborhood graph construction is necessary. So here, SNE, t-SNE, and UMAP also belong to this category. So they operate roughly in the same way. First, you want to compute a high-dimensional probability matrix between I and J, the 2 data points. And based on that, you want to compute low-dimensional probabilities that can best approximate the high-dimensional probabilities. And by approximation, we need to define a cost function that measures the differences between the 2 sets of probabilities. And then we minimize the cost function. That's the idea. So first of all, step 1 is to calculate high-dimensional probabilities. This is something we briefly touched at the end of last lecture. We start by computing the probability Pj given I, that data point I would pick another point j as its neighbor. So essentially, you need to have a distance from I to j, and that's called dj given I, or it could be some other dissimilarity, but it's basically the square of the distance or similarity. And I think in the standard way of using SNE, it's the Euclidean distance between data points I and j. So you're basically calculating this, transform distance square into this Gaussian density-like function. So when the distance is 0, this function value takes its maximum, e to the -0, that's 1. And if the distance goes larger, then this function value decreases down to 0. And you're calculating this for every neighbor j. And you normalize that by the total, the sum. So you sum over the neighborhood so that you will have the, oh, not, let me see. No, you don't summarize, you basically sum over all data points that are not equal to I. So therefore, this Pj given I, if you take the sum across all j that are not equal to I, then you will get a sum of 1. So this is a probability of data point I taking other data points as its neighbor. Okay. And for this dj given I, it can be some scaled Euclidean distance. So xi minus xj, the double vertical lines means the L2 norm. We take the square or Euclidean distance, and we just divide by the standard deviation we specify for sigma I. So this is like the Gaussian density. Sigma is the standard deviation, and xi is treated as the mean. And we're getting the density for xj following this Gaussian density surrounding I. And the mathematical intuition here is, given 2 points x, xj, the farther they are, the higher the distance dj given I, the higher their dissimilarity, and the lower the probability that they will consider each other neighbors. The key concept here is the further away two embeddings are in the space, the more dissimilar they are. Okay, so basically we convert Euclidean distances to some probability where if j is close to I, then j is more likely to be picked as a neighbor. Note that the dissimilarities are not symmetric due to the parameter sigma I. Okay, because that means if you have Pj given I and Pi given j, they're not the same. They're not equal to each other because Dj given I involves the standard deviation of data point I, sigma I squared, sigma I. And for Pi given j, here Di given j will involve sigma j, and that's specific to point j. They may not be equal. Okay, in practice, the user sets the effective number of local neighborhoods, or important concept, perplexity. This is a hyperparameter to be used in t-SNE as well. Once the perplexity k is chosen, the algorithm finds sigma I by a binary search to make the entropy of the distribution over neighborhoods equal to log 2k. What does this mean? So essentially, this H stands for Shannon's entropy, and Shannon's entropy measures the uncertainty of a distribution. So here we have a distribution with how many values? So taking I as the center, there are n minus 1 other data points, right? So each j can go from the first neighbor to the n minus 1th neighbor. So there are n minus 1 of such j. And we're calculating the probability of I picking j times the log of the probability of I picking j. So this is the definition of Shannon's entropy. So we're calculating this entropy across the n minus 1 probabilities. And essentially, you call this k. Okay, you call this log 2k. And so if you just transform k to be on the left-hand side, then it's essentially, based on the last equation here, k equals 2 to the power of the entropy. So the idea is that by changing sigma I, back here, by changing sigma I, you will for sure change the probabilities P of j given I. Okay, and then you will change the entropy. And so essentially, if you change the sigma I until you have this equation equal to your preset k. So k is the perplexity you set. And you want to, and it's like the bit. So Shannon entropy measures a bit. And so you know the concept of bit in computer in the computer storage. the related, irrelevant to the term, here I just want to say that the perplexity K essentially determines the neighborhood size. Why is that? So the entropy is actually monotone with K. So the larger the perplexity, the larger the entropy you allow. And larger entropy means that your distribution is more uniform. So uniform distribution has the largest entropy. And that means if you put a very large standard deviation neighborhood size here, the more data points will receive similar weights, similar probabilities, which will make the distribution more like uniform. While on the other hand, if sigma 1i is very small in the Gaussian standard deviation, then only very close by data points will receive a positive non-zero probability. Most of data points will have zero probability. So that will make the distribution of the n-1 values very far from being uniform. So that's why the entropy is small and perplexity is small. So essentially, the perplexity here determines the neighborhood in your PJ given I calculation. And the mathematical intuition here is the higher the perplexity, the more likely it is to consider points that are far away as neighbors. So the neighborhood size is bigger. One question may arise: if the perplexity is user determined, how do we know which one is correct? This is where art meets science. The choice of a perplexity is crucial for a useful projection into a low-dimensional space that we can visualize using a scatter plot. If we pick too low of a perplexity, clusters of data points that we expect to be together, given their similarity, will not appear together, and we will see subclusters instead. On the other hand, if we pick a perplexity too large for our data set, we will not see correct clustering. Since points from other clusters will be considered neighbors, there isn't a definite all good value for the perplexity. However, there are good rules of thumb. So essentially, I just want to add one thing, that because of the time limit, I'm not going to present our work for optimizing the perplexity, but my group indeed developed a method called SED, which is designed to preserve mid-range neighborhood, and it is a way to help you choose the perplexity. Okay, then back to the theme, SNE. Suppose that you already calculated the high-dimensional PJ given I without doing the dimension reduction yet. The second step is to calculate the low-dimensional probabilities. So here you want to define low-dimensional probabilities using the low-dimensional embeddings. So yi is the embedding for xi. So yi is two-dimensional. So following the same logic of using the Gaussian density, we define the low-dimensional probability of I picking j as its neighbor based on this. But here we want to have the neighborhood to be more even. So that is, we don't set data point I to have its own specific sigma I in the low dimensions. We instead just set all data points I to have the same standard deviation. So that's why in the density function, we don't have that dividing to sigma thing. We just set every sigma I squared to be 1/2. So we have a denominator of 1 in the density function's exponent. So then the low dimensional probability only depends on this low dimensional Euclidean distance transform into density. So there's no fixed variance, no perplexity parameter. So cost function. So we hope to measure the difference between the two sets of probabilities, and the Kullback-Leibler divergence, KL divergence, is a typical loss function to measure the difference between two probability distributions. Each point in both high and low dimensional space has a conditional probability to call another point as its neighbor. Hence, we have as many loss functions as we have data points. We define the cost function as the sum of the KL divergences over all data points. So sum over I, sum over j. So for each point I, we're looking at the KL divergence between Pj given I and Qj given I. And the KL divergence defined in this way means that we treat Pj given I as the reference distribution. And we just try to evaluate how the other distribution Qj given I deviates from Pj given I. The algorithm starts by placing all the yi in random locations very close to the origin, and then it's trained minimizing the cost function c using gradient descent. Details about differentiation and the cost functions beyond the scope of this post. So essentially, when they try to minimize the c function, the goal is to find minimizers as yi, yj for all the i's. So because these are the unknown values in this cost function, everything else is known. So pj given I is known because based on the data, we can compute pj given I. Qj given I depends on y and yj. So basically, y and yj will enter the cost function through qj given I. By taking the gradient against each yi, we can solve for the minimizer of the cost function, and that will be our y1 to ym. But and gradient descent is a typical way for optimizing an algorithm function. Okay, so KL divergence. If this is something new to you, we'll do a quick review here. It is a measure of how one probability distribution diverges from a second reference probability distribution. It is often used in statistics machine learning to measure the difference between two distributions. Here's an intuitive explanation. Okay, so probability distributions, we have two of them. P is the true distribution, Q is the approximate distribution. So in our case, P is the high dimensional distribution, and Q is what we try to get in the 2D space, Qj given I. Information loss. KL divergence quantifies the amount of information loss when Q is used to approximate P. This is it. So P is the true distribution and Q is the approximate distribution. So if P and Q are both discrete, taking a finite set of values, this is the KL divergence. And this is a continuous version. But please note that the KL divergence is not symmetric. So Q divergent from P is different from P divergent from Q. And it is always non-negative. Okay. There's an issue with the use of KL divergence in SNE, and that's why we need some improvement. If two points are close together in high dimensional space, their dissimilarities, the dj given I, are low. The probability should be high, right? Pj given I should be close to 1. Then, if they were mapped far away in the 2D space, the low dimensional probability would be low. So then Q doesn't mimic P well. In this scenario, we see that the loss function takes very high values because Q is very different from P, severely penalizing that mistake. On the other hand, if 2 points are far away from each other in high dimensional space, their dissimilarities are high and the probability should be low, P close to 0. Then if they were mapped near each other in the 2D, then the low dimensional probability will be high, close to 1. So we can see that the KL divergence is not penalizing this mistake as much as we would want. This is the key issue will be solved by UMAP. So essentially, this is measuring the KL divergence. This is the theoretical KL divergence without running t-SNE, just showing that it has some issue. So we know it's not symmetric. So here, just take a look at how we have for different, you need to have some 3D imagination here. So how would the KL divergence change when P and Q differs? So the first scenario is P is 1, Q is 0. So P is 1, Q is 0. It's this point, right? And we see the KL divergence is large. This is good. It means that it will make our cost function high. This is what we want. But the other end, P is 0, Q is 1. So it's this one. P is 0, Q is 1. It should also be penalized in the cost function. However, you see it's not penalized much. So this has a small value, which doesn't make a large contribution to the cost function. So this means that when we look for the low dimensional embeddings, we will prevent the first case. That is close points being far away in 2D. That won't happen because we penalize it. However, the other extreme, for faraway points, we may mistakenly put them close to each other. So that's what that means. Faraway high dimensional points are close in low dimensional space. This doesn't receive much of a penalty. So that's why this is an issue with the SNE. It doesn't prevent this. We may have 2 points that seem to be close to each other in 2D, but their original high dimensional points may be far away. Okay, so SNE, and this will be solved by UMAP, just bear in mind. Okay, T-SNE. At this point, we have a good idea of how SNE works. However, the algorithm has 2 problems that T-SNE tries to solve. Its cost function is very difficult to optimize, and it has a crowding problem. So yeah, more on this below. 2 main modifications are introduced by T-SNE to solve these issues: symmetrization and the use of t-distribution for the low-dimensional probabilities. These modifications arguably make T-SNE the state-of-the-art for dimension reduction for visualization for many years until UMAP came along. So first one, symmetric SNE. So the first modification is the use of a symmetrized version of SNE. Generally, the conditional probabilities described so far are not symmetric, right? Pj given I is not Pi given j. This means that the probability of point xi to consider point xj as its neighbor is not the same probability that point xj would consider point xi as a neighbor. We symmetrize pairwise probabilities in high-dimensional space by defining this Pij, which is Pj given I plus Pi given j divided by 2 divided by data points m. This data definition of Pij is such that every data point xi makes a non-negligible contribution to the cost function. You may be wondering, what about the low-dimensional probabilities? So basically, you just have Pij instead of Pj given I or Pi given j. So I and j become symmetric. And to solve this, the second main modification introduced the use of a student t distribution. And this is what the t means in T-SNE, with 1 degree of freedom for the low dimensional probability instead of using the Gaussian. So remember, this Qij previously is this. Take a look. Is this. So we're using the Gaussian density in the original SNE for Qj given I. But now we are just using the density function for t distribution. Okay. So this will make that we also define in the symmetric way. So the main advantage is that if you want to calculate the gradient for the cost function, symmetric cost function has a simpler form and much easier and faster to compute, improving performance. So, but you're still using the KL divergence. So the problem here still exists. That is, you may have 2 faraway data points in high dimensional space to be close in the 2-dimensional space. This is not to say that it is completely ignored, but the main takeaway is that T-SNE severely prioritizes the conservation of the local structure. Okay, so intuition. Since the KL divergence function does not penalize them, I just said this already, the misplacement in low-dimensional space of points that are far away in high-dimensional space, we can conclude that the global structure is not well preserved. T-SNE will group similar data points together into clusters, but distances between clusters may not mean anything. Finally, UMAP, a graph of similarities. Unlike T-SNE that work with probabilities, UMAP work directly with similarities. So it defines this high-dimensional similarity. So there's one thing that you need to pay attention to. So unlike what we have in SNE, which is, just go back a few slides here. Okay, you have the exponential negative distance square, right, as the similarity. So in UMAP, you just have the distance, you minus a rho I for this data point I, divide by sigma I. So there are some differences in being square or not, and also subtracting this additional constant specific to I. And it defines low-dimensional similarities Wij in this way. So you can also see some similarity with the t-SNE, right? 1 plus Euclidean distance raised to power 2b multiplied by a and inverse. If you go back to t-SNE, this is what we have. So here the difference is that you don't have the a here, you don't have the b in the power. But other than that, it's the same thing. So it seems that UMAP introduces more hyperparameters compared to t-SNE. Okay, and there's a key thing. Note that in both cases, there's no normalization applied. So we are not trying to normalize things to become probabilities that sum up to 1, unlike t-SNE, with a corresponding improvement in performance. The symmetrization of the high-dimensional similarities is carried out using probability T conorm. So you're trying to do this symmetrization also to make it symmetric. In addition, and this symmetrization is also using t-SNE. In addition, UMAP allows for different choices of metric functions D for the high-dimensional similarities. We need to address the meaning of rho I and sigma I here in defining the high-dimensional similarity rho and sigma I. The former represents the minimum desired separation between close points. That's the main dist hyperparameter in SURAT in the low-dimensional space. And the latter, the sigma I, is said to be the value such that you have something similar to perplexity in t-SNE. Yeah, so basically, where case the number of nearest neighbors, you set this, and then you go back, reversely solve for sigma I, given rho I. So therefore, both rho and sigma are hyperparameters, which will affect how you define the similarity, local similarity. So essentially, rho I is added, which is something not in t-SNE or SNE, but only in UMAP. It's just the minimum distance you want to have. But the sigma I carries similar thing as the perplexity in the t-SNE. Okay, in the optimization phase of the algorithm UMAP, the creators of UMAP made some design decisions that played a crucial role in its great performance, including, okay, first thing, most importantly, KL divergence is changed to something called cross entropy as a loss function. While t-SNE uses KL divergence, the cross entropy loss function has both attractive and repulsive forces, while KL only has attractive. It is worth noting that t-SNE has repulsive forces, but not on the loss function. Okay, the repulsive forces appear in the renormalization process of the similarity matrix. However, global renormalization is very expensive. UMAP has it simpler by using cross entropy loss and with better results on preserving global structure. With this new choice of loss function, place objects that are far away in high-dimensional space nearby in the low-dimensional space is penalized. That's something SNE and t-SNE don't do. Thanks to the better choice of loss function, UMAP can capture more of the global structure than its predecessors. Second, UMAP used stochastic gradient descent to minimize loss cost function instead of a slower gradient descent. So computational efficiency is another game. Okay, so finally, what is cross entropy? Here it is. Cross entropy is a measure of the total number of bits needed to identify an event from a set of probabilities if a coding scheme is used for the set is based on given probability distribution Q rather than a true distribution P. So you still have two distributions. One is true, one is what you use. So KL divergence means, okay, if you use Q instead of P, what is the information loss? But cross entropy doesn't have that. Essentially, you see here in the cross entropy, if you take a look, okay, so minus sum over pi log qi. Compared to here, you have minus pi log qi. But you also have a term which is pi log pi. So basic KL divergence is pi log pi minus the cross entropy. So cross entropy is the second term in the KL divergence. So essentially, you can see cross entropy is equal to KL divergence plus the entropy of P. Okay, so essentially you have the KL divergence involving an additional term that the cross entropy doesn't have. So what does the function form look like? This is the thing. So you see, if you look at how the cross entropy changes with P and Q, previously, only when P is 1, Q is 0, we have a large KL divergence. But now, you see, when P is 0, Q is 1, which we also don't like, also has a large cross entropy, but it doesn't have a large KL divergence. So that's why using cross entropy will penalize for putting faraway data points close together. Okay, so finally, we want to do some comparison of t-SNE, UMAP, these kind of preserving local probabilities or local similarity approaches versus the ISOMAP and LLE. So t-SNE, UMAP preserve local structures, and t-SNE for local structure, UMAP is doing better with global, while ISOMAP is global, LLE is local. Most importantly, the old methods are much slower, right? While the newer method, they have just one loss function, cost function to minimize. They can use techniques like stochastic gradient descent to make it faster. Yeah. And for the quality, t-SNE and UMAP, because of their preference for preserving local similarities, you will see the local cluster visualization, which is something you won't see in ISOMAP and LLE. And because single cell data from many data sets, we just have cell types. That's why we want to see cell clusters. And that's why we want to look at t-SNE UMAP. While these older methods are more for finding the manifold. And this is something good to pay attention to, the perplexity. So t-SNE, you can have as n squared, or you can go faster to n log n. And UMAP is n log n. But ISOMAP and LLE typically n cubed, so that's why it's very slow. And sensitivity to parameters, t-SNE sensitive to perplexity, UMAP to the number of neighbors and the minimum distance, while ISOMAP and LLE are insensitive to the neighborhood size, the K you use to construct the graph. Okay, this is the method my group developed for optimizing the hyperparameters. So since we still have a little time, I'll just quickly say that. So the idea we want to use is to look at a point's neighbors before you do the embedding. We call them pre-embedding neighbors in the original input space versus its neighbors in the 2D space. So we want to just have a way to measure the similarity between the two sets of neighbors. So what we do essentially is to take the ordered neighbors from the farthest to the closest in each space and record each neighbor's 2D Euclidean distance to the cell in each space. So you see that here we will have an ordered 2D distance vector. So this is based on the 2D neighbors, farthest to closest, its own ordering, and we just record the 2D space, a 2D distance we see in the figure. And for this one, we take the high dimensional space, the original input space, order from farthest to closest. And we also use the same figure, 2D figure, to get the 2D Euclidean distances. And the goal for doing this is because when we visualize the figure, we only look at the 2D space, right? So the Euclidean distances are something we try to interpret. And also something good to know is we want to preserve the mid-range neighbors. So here, the neighborhood size is half of all data points. So then we just calculate a Pearson correlation between the two distance vectors. If it's high, we say this cell one's embedding is reliable because it's reliable that its neighbors don't change much after embedding. And this is a bad example. We want to say that the cell 2 is not reliable just because its pre-embedding neighbors are very, very different from its neighbors in the 2D space. So in this, the reliability score between its two distance vectors is low. So the key thing here is for us to decide on a threshold on the reliability score. How high is high, how low is low? If it's too low, then we will flag this cell as not reliable. We call it dubious embedding. So then we make a story of our figure. We shouldn't do that. So the permutation is a technique we use to generate the null distribution for reliability scores. So what we did exactly is to randomly permute all genes randomly permute a gene's values across all cells, and we do that for each gene. So this will make the cells called permuted cells, and such cells have no relationship with one another. So they are all equivalent because of permutation. So the neighborhood or relationships are not meaningful. So we're using that data and we calculate reliability score to give us an idea of the null distribution. Because the score is Pearson correlation, we know its range is from -1 to +1. So the values are comparable to these original cells scores. So using this, we can basically decide on some cutoff based on null distribution. So our idea is that if a real cell's embeddings reliability score is more than most of the null scores, we call it trustworthy. Otherwise, we don't think so. On the other extreme, if a real cell's score is even lower than most of the null scores, then it's too bad. Then we flag as dubious. And for the middle part, we'll see how many of the real cells lie in the middle, and they're more like the gray zone. But just for your information, the 5% here is based on the null distribution. It's not based on the real scores. So it doesn't mean that we can only classify 10% of the real scores. Instead, we can see that most of the real scores are actually in the right tail, which means that they're good, which is something we're happy to see. But we also see some scores to be in the lower tail. They're really bad, right? Really low, and we want to flag them so you don't make a story out of them. So that's for a given setting, given hyperparameter, we can detect the dubious embeddings. And if we have multiple hyperparameter settings, we can run our method to detect dubious embeddings and then find the minimum setting with whose dubious embeddings are minimized. So this is one figure from our paper, which just shows that, okay, this is the original t-SNE visualization where we have these 3 clusters in this relationship, and they are labeled in different ways, like ectodermal epithelial single cells. And this blue is the so-called neuron EC1 embeddings, and this neuron EC1 embeddings. So basically, they receive the same label, but they are separate in the visualization. And after we optimize our embedding, you see now they are unified down here as one cluster instead of being separate. So you see a very different visualization, and also how far away these neuron EC1, I think ectoderm cells, are from these epithelial cells. They used to be very close to each other, but now they're very far away from each other. So there is a Nature Method Perspective article that discusses how to use t-SNE and map in UMAP. What are the cautionary messages we need to pay attention to, because we cannot just blindly use the methods to tell a story. We need some checks. So that's pretty much what I want to say today. And this is the last slide. So any questions from our students? So t-SNE, UMAP are most widely used for visualizing single cell data, but I just want to say that they should be used just as visualization methods, not beyond that. So you cannot say they are clustering methods, they give me clusters. And sometimes the cluster they show may not be real clusters in the data. So you need some parallel checks by checking your data, by looking at, for example, gene expression heat maps to see whether the cells really look like a distinct cluster. Okay, so that's all for today. And so as I said in the beginning, for Wednesday, you will have a tutorial for the final project. And then I'll see you next week for the final project presentation. And we'll do it on Zoom, so people will have some flexibility if they're traveling. Okay, so thank you. And just let me know if you have any questions.